So plane strain condition. T of x, T of y and T of xy are present. Then dz is equal to xz is equal to yz is equal to 0. T suffix z is not 0. T is equal to epsilon tx plus tx. So substituting tz in equations, then Vx equal to Tx by E minus epsilon Ty by E minus epsilon square Tx plus Ty by E. So Vy is equal to epsilon Tx by E plus Ty by E minus of epsilon square Tx plus Ty by E. So Vx is equal to Tx by E 1 minus epsilon square minus Ty by E epsilon 1 plus epsilon. Vy is equal to minus Tx by E epsilon 1 plus epsilon plus Ty E 1 minus epsilon square. So multiply x by epsilon and y by 1 minus epsilon. So epsilon v of x is equal to Tx by E epsilon 1 minus epsilon square minus Ty by E epsilon square 1 plus epsilon. So 1 minus epsilon into v suffix y is equal to minus Tx by E epsilon 1 minus epsilon 1 plus epsilon. So 1 plus Ty by E 1 minus epsilon square. Then we can return as 1 minus Tx by E epsilon 1 minus epsilon square plus Ty by E 1 minus epsilon whole square epsilon square, from which we can we can get the final solution in terms of epsilon Vx plus 1 minus epsilon into Vy divided by 1 plus epsilon is equal to Ty by E from the bracket minus epsilon square plus 1 plus epsilon square minus 2 epsilon. So Ty is equal to E epsilon Vx plus 1 minus epsilon into Vy. So 1 plus epsilon 1 minus 2E. Similarly, x is equal to E into 1 minus epsilon into Vx plus epsilon into Vy 1 plus epsilon 1 minus 2E. X is equal to E into 1 minus epsilon Vx plus epsilon into Vy divided by 1 plus epsilon 1 minus 2 epsilon. So Txy is equal to E into 2 into 1 plus epsilon xy. You can write it in the matrix form. So Tx, Ty, T of xy. So E is equal to 1 plus epsilon 1 minus 2 epsilon. 1 minus in matrix form 1 minus epsilon 0 0 1 minus epsilon 0 0 0 1 minus 2 epsilon by 2 Vx x of Vx Vy x of xy. It is difficult to represent the curved boundaries by straight edge elements. A large number of elements may be used to obtain reasonable resemblance between original body and the assemblage. Two-dimensional problems. So general stresses and strains structure consist of two set of components Sx, Sy, Sz, T of y xy, T of y z, T of z x is for stresses. So E of x, E of y, E of z is equal into G of xy, G of yz, G of zx is for strains. So under contained conditions, the state of stresses and strains can be complicated, and finally it gets simplified. A general 3D structure analysis can therefore be reduced to two-dimensional elements. So the plain 2D problem is converted like this Then a long structure with uniform cross section and transferring load along its length, that is a direction. Stress strain temperature relation for elastic and isotropic materials, we have E of x is equal to 1 by E n by E 0 s suffix x is a strain suffix x then 0 strain at y plane n by E 1 by E 0 s suffix y E suffix y 0 then g of xy, so 0 0 1 by g tau of xy g of xy 0, where E naught is the initial strain, E the Young's modulus, n the Poisson ratio, and G shear modulus. So G is equal to epsilon 2 into 1 minus n. Which means that there are only two independent materials constants for homogeneous and isotropic material. We can also express stresses in terms of strains by involving the above equation. The above relations are valid for plane stresses case. The plane strain case, we need to replace the material constants in the above equation in the following fashion. So n 1 minus n, where alpha is the coefficient of thermal expansion, then T is the change of temperature. Note that if the structure is free to deform under thermal loading, there will be no stresses in the structure.